In this video, we introduced the last two pieces of new vocabulary for quantified logic. So remember, we have left over variables and quantifiers. Now these two are going to go hand in hand, so I'm going to sort of introduce them together. So recall from our last video that we have predicates and we translate them usually with this like partial sentence kind of structure where they have blanks that we can fill in with constants, which are like names are one kind of constant, or definite descriptions were the other kind of constant. So we can put constants in the blanks of predicates. So if we want to say like Fabio is a student, we have SF, Jessica is a student, we have SJ. Now these sentences are about specific people. But sometimes we want to make claims about non-specific people. What if we want to say something like everyone is a student or no one is a student? How would we go about that? It seems like we need some kind of placeholder that fills in for all of the people, and we say everybody is a student. The way we do this is with a variable. So when we want to talk about a non-specific individual, we want a placeholder that says every individual can fill this role. So everyone is a student. We want to translate it as something like SX, where any individual or every individual can play the role of X. X here is a variable again because it stands in for a number of possible values. It could be anybody that I'm talking about. But just saying SX doesn't actually yield any definite meaning. It tells us that X is a student, where X signals a role that can be played by an individual, but it doesn't tell us who plays this role. Is it all individuals? Is it just one individual that plays this role, or some individuals, or maybe nobody? So when we have this kind of placeholder, because we're not picking out somebody or saying it holds of some number of people or something like that, it doesn't yield a definite meaning. When this happens, when we have a variable in a formula, but it's unclear who plays the role that it signals, we say that the variable is a free variable. So this means that the logical formula SX is well formed, but it's not actually a proper sentence. What we call it is an open formula. So you might be wondering, well, how do I go from an open formula to a well-formed sentence? We need to introduce the quantifiers to do this. Quantifiers, or why quantified logic is called quantified logic, are going to help us specify what individuals can play the role of X, and we're going to add them to the start of some kind of open formula. So we're going to learn two of them. The first is what's called the universal quantifier. We read this as for all. The notation is that it's an upside down A. In Carnap, you will type just a normal A. So a right side up capital A is the translation in Carnap, but if you write it by hand, it is an upside down A. This tells us that all individuals in the domain can play the role of the variable. So everybody that I'm talking about plays the role of the variable. Everybody is a student, something like that. We again read this as for all. And the second one is the existential quantifier, and we read this as exists. The notation is that it is a backwards capital E. So in Carnap we write it as a forwards E, capitalized, but if we're writing it by hand, it's a backwards E. And it tells us that there exists at least one individual in the domain that can play the role of the variable. So suppose I want to say something like everyone is a student, I would write out for all X, SX. And this says that every individual can play the role of X. And SX tells us that the role of X is to be a student. So if I wanted to represent this visually, I'd say, well, suppose I have three individuals in my domain, then all of them are students. They're all in the student camp. There are no non-student individuals. Okay, here's another example. If I want to say there exists a student, all I need is that one individual is in the student camp, and that it doesn't really matter how many are in the non-student camp. So I would write this as exists X, SX, excuse me. And this says that there exists an X that can play the role of being a student in my domain. Now, I could have had two individuals be students, or even all of the individuals be students. these are all perfectly fine because there still does exist a student. So if no individuals were in the student camp, that's when exists X as X would be false. Okay, so more definitions for you. We call an occurrence of a variable in a formula, which is in the scope of the quantifier, a bound variable. So when there's a quantifier that specifies which individuals play the role of the variable is called bound. Just the same thing. A free variable is an occurrence of a variable in a formula which is not a bound variable. So we just define it as the opposite. So an open formula is something that we get from removing the quantifiers of a quantified well-formed formula. This is the definition your book gives, so you can compare this to the one that I gave before. So Sx is like as it stands on its own. It seems like we removed some quantifiers from the start of it to get it. So if we had something like exists x Sx and took off the exists x and just had Sx, then we would have this kind of open formula. The opposite of this is a closed formula or a sentence, and this is formed when a formula has no free variables. This means that it has only constants or all of the variables are bounded with quantifiers. In these cases, we call it a closed formula, also known as a sentence. Okay, so that's all the vocab that we need to go forward. Okay, so you might be wondering, what is the relation between the existential quantifier and the universal quantifier? So to consider this, suppose you have the sentence, someone is a student. So we can represent this as with this diagram. So there is at least one student, so someone is a student is satisfied by this diagram. We could translate this as saying that exists X as X, so there exists a student. But we could also translate this as saying that not everybody is a non-student. So what I'm saying here is that not everybody falls in this non-student camp. There is at least one person that falls in the other camp. So you'll note that I slipped there between using the universal, not everybody is a non-student, to using the existential, there is at least one person in the other camp. What this tells us is that these quantifiers are interdefinable. So these two expressions, exists X, Sx, is equivalent to negation for all X, negation Sx. So there are loads of different equivalences of quantifiers that we'll learn as we move to proof rules, but I wanted to introduce this to you because I think it's pretty intuitive to see the relation between these. So exists a student and not everybody is a non-student. And when you start your translations, you might get caught up in, well, should I use a universal or an existential? And this is just to say there are loads of cases in which these two will be equivalent. In other words, they're both going to be correct because quantifiers are interdefinable. Okay, so now we're going to talk about how to form well-formed formulas in quantified logic. And for that, we need to understand better how the bounding works on these quantifiers. So each quantifier bounds one variable in the well-formed formula that follows it immediately. So if we have something like for all x, px, the universal here bounds the x in px, and px is a well-formed formula. We can also consider for all x, parentheses, px and qx, the universal here bounds the x in both px and the qx, because the well-formed formula that follows it is just this whole combination of px and qx. So we can have entire well-formed formulas where the variables that occur in that well-formed formula is bound by the quantifiers that come before it. What we can't have is something like for all x, px, and qx. Here, the universal bounds only the x and px, but with the qx, that's just a separate well-formed formula where x is appearing as a free variable. So we would have to put some kind of parentheses around this if we wanted to bound the free variable occurring in the qx. So all variables in the well-formed formula that immediately follow a quantifier are considered to be in the scope of that quantifier. So with the previous example, the x that occurred in the qx was not actually in the scope of the universal quantifier that occurred at the start of the expression. Quantifiers only bound variables within their scope, so with whatever is in the well-formed formula that comes immediately after it. At this point, we're in a position to see the well-formed formula rules of quantified logic. So a well-formed formula of quantified logic is constructed using the following rules. The first is if you have P, some kind of n-place predicate, and some names m1 to mn, then P m1 ... mn, just a list of these names, is a well-formed formula. Note, if you have a two-place predicate, you require two names to fill in the blanks. If you have an n-place predicate, you require n names. And the second rule is if you have phi and psi as well-formed formulas, then any combination of them using our sentential connectives, like and, or, if, then, etc., is a well-formed formula. In other words, all of the sentential logic rules still hold. And then finally, the one for quantifiers. If phi is a well-formed formula and m is a name occurring in it, then if you put a universal for all x phi whatever, or an existential exists x phi whatever, these are well-formed formulas. So I've indicated phi star as the result of replacing the names, m in this case, with the variable x in the expression or the well-formed formula phi. So what you do is you have some kind of expression like PA, and then if you want to turn it into a universally quantified expression, you replace the a with an x, and then you put for all x out in front of it. So then you'd have for all x px. So what I've done is I replaced the name with the variable. You'll have a few exercises asking you to do this replacement just to get used to what it feels like. It's really quite simple to do the replacement. You just replace every occurrence of a name with some particular variable you've chosen. With all these well-formed formula rules, we can now talk about what it means to identify the analogous of the main connective in quantified logic. So we can't actually talk about the main connective anymore because it could be a quantifier that's the last thing added, and so we say is the main operator. So the connective or the quantifier that's the last thing to be added is the main operator. So here's some examples. The main operator of exists x px is the existential quantifier. The main operator of negation of exists x px is the negation. And then finally, the main operator of the expression exists x px and for all y qy, because there's no parentheses around it or anything, is actually the conjunction in the middle. The main operator, like the main connective, tells you what the sentence is about. So if you had for all x, px, and qx, this means that the sentence is about everybody being such and so, having some properties. Another example, so if you take the for all x, px, and then you have an and qx, but you don't have the parentheses, this means that it's telling you about two things both being true. Okay, so in the following now, I'm just going to go through a bunch of different examples of how to use these quantifiers in translation, and then you'll have a lot more in your practice problems for this week as well. So let S be the predicate is a student. Here are some of the cool well-formed formulas we can make with the existential quantifier. So very simply, exists x px tells us that there exists somebody who is a student. Exists x negation px says that there exists somebody who is not a student. If you move that negation to the start and you have negation of exists x px, that means that there doesn't exist anyone who is a student. We'll see the translation of this with the universal might be a little bit clearer. So if we say it with two negations, we have negation exists x, negation sx. This says there doesn't exist anyone who is not a student. What about exists sx, sx, and exists y, negation sy? Well, this we can translate in two parts. So we do the first part first and then the second part, and we put them together with the conjunction. So for the first part, we have the same thing as we had above. There exists someone who is a student. For the second part, we have actually the same thing as on the second line. There exists someone who isn't a student. And then we just put them together. So we have there exists someone who is a student and there exists someone who isn't a student. We've not said anything about what the relation between these two someones is. They could be, well, they'll likely be different people. But the idea here is that because we've used two different variables, we haven't said anything about the relation so far. The last one here is exists as Sx or negation Sx. So here we have there exists someone who is either a student or isn't a student. We put the existential out front and then we had a disjunction in the parentheses. Okay, so now I'm going to go through some of these kinds of style of translations with the universal quantifier. So same thing, we have a one-place predicate is a student, and another one-place predicate for is tall. Here are some of the cool well-formed formulas we can make. If we say for all s Sx, now we've switched to the universal quantifier, which means that we translate this to everyone is a student. What about for all s negation Sx? Here we have everyone is not a student. You might also translate this as no one is a student. What about negation of the universal Sx? So we have negation for all x Sx. This means that not everyone is a student. If we have a double negation, so we have negation out front and inside, we have negation for all x, negation Sx. This translates as not everyone is a non-student. Here's another example. Here we're introducing that one-place predicate is tall. Here we have for all x, if Sx, then Tx. So this would translate it as everyone who is a student is tall. So if you're a student, then you're tall, and that applies to everyone. That's how I would read that translation. And then finally, what about something like negation for all x, Sx, and Tx? This says not everyone, so that's what the negation of the universal out front is, and then inside the parentheses is both a student and is tall. So we have that conjunction inside. Okay, so I'll just note that some of these seemed like equivalent translations. So we had this sentence, there exists someone who is a student. This is equivalent to saying that not everybody is a non-student. And so you can compare the two different translations with the different quantifiers out front if you like. Similarly, there exists someone who is not a student, means that not everybody is a student. These are equivalent. And there doesn't exist anyone who is a student is equivalent to everyone isn't a student. In other words, no one is a student. And there are loads of other different equivalences you can draw. Okay, so let's do a few more trickier translations and then we'll conclude. So let S be the one-place predicate is a student and A be the constant Alice. This means that if we have something like SA, we are saying Alice is a student. If we have something like exists X, SA, and SX, we're saying Alice and someone are both students. Note here that this is equivalent to saying SA and exists X, SX, where the SA is outside of the parentheses of the existential quantifier. Because SA doesn't have a variable in it, it's not actually affected by the existential quantifier because that only acts on the X variable. Another note is that if there's only one student and that student is Alice, the above sentence would still be true. This is because SA is true if Alice is a student, and exists X, SX is true if Alice is a student because there exists a student, and so the conjunction of these is true. We haven't said so far that Alice is not the same person as the student picked out by the existential. We'd have to further specify that if we wanted to. So here's another example. Consider the sentence, everyone who's younger than a student is also a student. Well, it seems like we're going to need two variables to translate this. So one is going to stand for is a student, and the other is going to stand for something about being younger than that student. So it's going to be something about the property of being younger. So without quantifiers, we can translate the sentence like, we can start the translation like, if X is a student and Y is younger than X, then Y is also a student. So that would mean something like SX and Y younger than relation YX. If both of those are true, then SY. And then finally, we put the quantifiers for the variables out front. So for all X and for all Y, SX and YX, if both of those are true, then SY. That's how we would translate everyone who's younger than a student is also a student. Okay. One more example for you. There's someone who likes someone. So a more natural expression might be there's at least someone here who understands the meaning of love. So how would we translate this? We'd have to translate it as two existentials out front of some kind of relation of liking. So exists X and exists Y such that likes XY or LXY. So there is at least one someone X who likes another someone Y, and they're put together with this likes relation LXY. Now note, when the quantifiers are of the same type, so existential here, the order of them doesn't matter. So we could have written exists Y and then exists X, LXY. Writing it doesn't matter much until we get to proofs in which the order will start to matter. We typically go in alphabetical order, so we'll usually put X and then Y and then Z for our variables, but it doesn't matter, like I said. And then again, one more time, we haven't required that X and Y be distinct in the above. So just because we said exists X and exists Y, that doesn't mean that X and Y are not the same person. So somebody could understand the meaning of love by, loving themselves. Okay. One more thing. So as promised, we were going to talk about the special logical relation, the equivalence. So remember this slide from last time. So what if you had multiple names? UCI goes by University of California, Irvine and University of the Anteaters. We said we would represent this by putting this special logical relation between the I and the A. So remember in this example, exists X, exists Y, LXY, we didn't require that X and Y be distinct individuals. So the sentence was true even if there was just one person and they liked themselves. If we want to be able to talk about liking other people, what we have to do is specify that X and Y are not the same individual. And the way we do that is we say exists X, exists Y. X is not equal to Y, so that's that equal sign, and we put a slash through it to indicate that they're not equivalent, and LXY. We write X equal to sign with a slash through it, Y, or X and Y are not equivalent to mean that negation of the equivalence of X and Y. Similarly, if we want to say that every student is taught by someone else, as in somebody who is not that student, we would say something like, for all X, if SX, if they're a student, then there exists a Y such that X is not equal to Y, and this teaching relation holds, TYX. So there's just another example of how to use that non-identity. Okay, so at this point, we've actually covered all of the vocabulary that we need of quantified logic, and we're in a good position to start doing some of our own translations and then move to models next week.